Most machines tell you when they're working. The rumble, the vibration, the low-frequency hum your nervous system has been quietly absorbing for years without you noticing. Tonight, we follow the car that removed all of that and what that silence does to the human body. If you have ever sat inside a Tesla with the car powered on but parked, you have experienced something that is genuinely unusual. There is no idle. There is no vibration passing through the seat or the steering wheel. There is no low mechanical pulse traveling up through the floor. The car is on. It is alive. It is doing things. And yet, your body cannot feel any of it. A conventional petrol engine, even at rest, is a machine at war with itself. Pistons moving against cylinder walls, valves opening and closing hundreds of times per minute. A crankshaft converting vertical movement into rotation. All of it producing friction, heat, and vibration that passes through the engine mounts, into the chassis, into the seat, and finally into the body of the person sitting inside. Most drivers have stopped noticing it, but the nervous system has not. That constant micro-vibration is physical information your body is processing at all times. And the moment it stops, people who sit in an electric car for the first time often feel a relaxation they cannot explain or name. At highway speed, independent testers at publications, including Car and Driver, have measured the Tesla Model S cabin at around 57 to 60 decibels. A typical petrol-powered luxury sedan at the same speed sits closer to 68 to 72 decibels. That might sound like a small difference on paper. In practice, because the decibel scale is logarithmic, 60 decibels represents roughly a quarter of the acoustic energy of 70 decibels. The Tesla cabin at 70 miles per hour is quieter than most offices. It is quieter than most restaurants. It sits in the frequency range that acoustic researchers associate with calm, sustained focus and easier entry into sleep. And the car is not simply quiet because the engine is gone. The engineers worked deliberately to fill that silence with nothing. The windscreen glass on the Model S is laminated acoustic glass, the kind used in recording studios. The door panels are lined with sound-deadening material. The floor is sealed. Even the door handles, which retract flush with the bodywork when not in use, were designed partly to remove the small turbulence that a protruding handle creates at speed. Every source of noise was identified and then, one by one, removed. While you sit in this silence, the car is not idle. The battery management system is monitoring cell temperatures. The thermal management system is running a quiet calculation about whether heating or cooling is needed. If the car is connected to a network, it may be receiving data. It is thinking, in its way, completely without sound. If you are watching this from your bed tonight, and the room around you has gone quiet, you are already experiencing something close to what a Tesla offers by design, a reduction in the noise your nervous system is asked to process. The engineers who built this car had a theory. Silence is not simply the absence of something. It is the presence of something else entirely. We will get to that, but before we follow the story of where this machine came from, take a moment to do something that the engineers who built the first Tesla specifically set out to make possible. Just rest. If this is the kind of story you want to fall asleep to every night, subscribe to Simple Science so you never miss one. Leave a comment below telling us where in the world you are watching from and what time it is where you are. We love knowing that. The silence you just heard about did not happen by accident. Someone chose it. 2 people, to be exact, and neither of them had ever built a car before. Martin Eberhard had spent most of his career thinking about how to store information. In the late 1990s, he co-founded Nouveau Media, the company that made the Rocket e-book, one of the first commercial e-readers. So Mark Tarpenning was a software engineer who had worked alongside him. They were not automotive people. They were energy people. And in 2002, they watched something happen that changed the direction of both their careers. General Motors recalled the EV1. The EV1 was an electric car that GM had leased to drivers in California and Arizona beginning in 1996. It was fast, quiet, and clean. People who drove it were devoted to it in a way that usually takes decades to build between a driver and a car. When GM announced it was ending the program and reclaiming every vehicle, some lessees refused to hand theirs back. There were candlelight vigils outside the lots where the cars were being collected. A small group attempted to buy the entire remaining fleet. GM said no, crushed the cars anyway, and cited maintenance costs as the reason. Says Eberhard watched this and came to a conclusion that was either obvious or radical, depending on who you asked. Electric cars had not failed. The batteries had. The battery technology GM used was nickel metal hydride. Heavy, expensive, and slow to improve. But Eberhard had spent years watching a different kind of battery get cheaper and better every single year. The lithium-ion 18650 cell. The same cylindrical cell inside a laptop. Energy-dense, light, and already being manufactured by the billions. His question was simple. What happens if you put thousands of them in a car? He and Tarpenning founded Tesla Motors on July 1st, 2003 in San Carlos, California. The name came from Nikola Tesla, the Serbian-American inventor whose AC induction motor they planned to use as the car's drivetrain. They had a concept, a name, and a theory. They needed money. In February 2004, a technology entrepreneur named Elon Musk led Tesla's Series A funding round, contributing $6.5 million of the $7.5 million raised. He joined as chairman of the board. At the time, he was also running SpaceX, which he had founded 2 years earlier, and Tesla had not yet built a single prototype. What Eberhard and Tarpenning had, and what Musk saw in it, was a premise that most of the automotive industry had dismissed as impractical. Not the idea of an electric car, which was old. The idea that laptop battery chemistry, assembled at scale and managed with the right software, could produce something that would make a petrol engine feel primitive by comparison. There is a footnote to this story that most people never hear. Martin Eberhard and Mark Tarpenning both left Tesla before the company became what it is today. Eberhard departed in 2007 after a period of disagreement with the board over production costs and timelines. Tarpenning left in 2008. Neither man was present for the launch of the Model S in 2012, the moment their original theory was vindicated at scale. Their names rarely appear in the popular history of Tesla, which is largely told as Elon Musk's story. The 2 men who decided, sitting in California in 2003, that laptop batteries could replace petrol engines are not household names. They chose to name the company after a man most people at the time knew only vaguely, if at all. A scientist who had died 60 years earlier, alone in a New York hotel room, with none of the wealth or recognition that his inventions probably deserved. And that man's story is the next one worth knowing. Nikola Tesla was born on July 10th, 1856, in the village of Smiljan, in what is now Croatia. His father was a Serbian Orthodox priest. His mother never learned to read, but could memorize entire books and recite them from memory, a talent her son inherited and built a career on. He arrived in New York in June 1884 with 4 cents in his pocket, a letter of introduction to Thomas Edison, and a head full of ideas about electricity that he had been unable to act on in Europe. Within months, he was working for Edison. Within a year, they had parted badly over a dispute about money and engineering philosophy that neither man ever fully resolved. The disagreement was not personal at its core. It was technical. Edison built his electrical empire on direct current, or DC. Tesla believed the future belonged to alternating current, or AC. DC is electricity flowing in one direction, like water through a pipe. AC reverses direction many times per second, and this property makes it far more efficient to transmit over long distances. Tesla was right. The electrical grid that powers nearly every building in the world today runs on alternating current. In 1887 and 1888, Tesla developed and patented his AC induction motor. The principle behind it is elegant enough to describe in a single sentence. A rotating magnetic field in the stationary outer ring pulls the inner rotor around with it, and nothing ever needs to physically touch anything else. No brushes, no contact points, no friction. The motor produces rotation from pure magnetism, and Tesla sold his AC patents to George Westinghouse in 1888 for $60,000 and royalty agreements that he later surrendered entirely, reportedly to help Westinghouse survive a financial crisis. He spent the following decades working on wireless power transmission, radio technology, and experiments so far ahead of their time that many were not understood or replicated until decades after his death. He died alone on January 7th, 1943, in room 3327 of the New Yorker Hotel in Manhattan. He was 86. His work had helped build the modern electrical world, but he died in debt, having signed away or lost most of his patents. The US government seized his papers and laboratory notes immediately after his death. In the decades that followed, his name appeared occasionally in engineering textbooks. He was not a household name. He was not on currency. See, he had no major monument. He was, in the way that certain foundational inventors become, invisible inside the things he made possible. When Martin Eberhard chose the name Tesla for his new electric car company in 2003, he was making an argument as much as a choice. The AC induction motor that Tesla patented in 1888 was going to power their vehicle. The least they could do was acknowledge whose idea it was. That motor, over a century after Tesla developed it in a New York laboratory, now sits inside millions of vehicles on roads across 6 continents. It still works by exactly the same principle: magnetism, rotation, silence. The next chapter is about what that motor actually does when you press your foot down on a Tesla accelerator, and why what happens in that moment is unlike anything a combustion engine can produce. A petrol engine produces torque gradually. Press the accelerator and the engine needs to reach a certain RPM before it is generating its full power. This is why you feel the car hesitate, then build, then surge. The power climbs a curve. You are waiting for chemistry to catch up with your foot. An electric motor produces its maximum torque at 0 revolutions per minute. The moment the rotor begins to turn, full force is available. There is no waiting. There is no RPM curve to climb. You press the pedal, and the response is, for practical purposes, instantaneous. This is not a marketing claim. It is a property of electromagnetism. The magnetic field that pulls the rotor around exists at full strength the moment current flows. In the Tesla Model S Plaid, 3 electric motors work in combination to produce a combined output of around 1,020 horsepower. So the car weighs over 2,100 kilograms. It still accelerates from 0 to 60 miles per hour in under 2 seconds, making it one of the fastest accelerating production vehicles ever measured. The motors in the Plaid operate at up to approximately 20,000 revolutions per minute, a speed that most combustion engines could not sustain without destroying themselves. But speed is almost beside the point here. The more interesting thing about the AC induction motor is what it does not do. A combustion engine has, depending on the design, somewhere between 200 and 400 individual moving parts: pistons, connecting rods, camshafts, timing chains, valves, a crankshaft, an alternator, a water pump. Each of those parts is touching another part while moving, producing heat, wear, and noise. Each of them requires oil to lubricate the contact. Each of them will eventually wear out. The AC induction motor in an early Tesla, like the Model S, has one moving part: the rotor. It spins inside the stator without touching it. The gap between the two is about 1 millimeter. Magnetism crosses that gap, and rotation happens. No oil is needed to lubricate the motor itself. No timing chain will stretch. No valves will stick. The simplicity is not a compromise. It is the point. Tesla has used different motor designs in different models over the years. The Model 3 and later Model S and Model X use permanent magnet motors in the rear, which are more efficient at steady highway speeds. The fundamental principle remains the same: magnetism producing rotation, cleanly, continuously, and nearly silently. When an early Tesla owner described driving their car for the first time, the word that came up repeatedly in reviews and owner accounts was not fast, though it was fast. It was not quiet, though it was quiet. The word was smooth. The torque delivery has no interruptions because there are no gear changes in the traditional sense, no clutch engagement, no moment where power is interrupted and reapplied. The car pulls with one long, unbroken force from the moment you accelerate to the moment you stop accelerating. That smoothness has a source, and the source is directly beneath the floor of the car, laid flat, invisible to the person sitting above it, holding enough energy to move 2 tons of metal over 300 miles without a single combustion event. What lives in that floor is next. Every car has a floor. In a conventional vehicle, the floor is structural: steel panels, cross members, a transmission tunnel running down the center where the gearbox and drive shaft pass through. It is engineering in service of packaging. The floor exists to hold everything else in place. In a Tesla, the floor is the point. The battery pack in the original Tesla Model S sits entirely flat between the front and rear axles, directly beneath the passenger cabin. In the 85 kilowatt-hour version, it contains 7,104 individual lithium-ion cells. Each one is cylindrical, 18 millimeters wide and 65 millimeters tall. the same format used in laptop computers, just slightly larger. They are arranged in 16 modules, each module holding groups of cells wired together in series and parallel to produce the right voltage and current. The whole assembly weighs approximately 540 kilograms. That weight, distributed evenly across the entire base of the car, sits at the lowest possible point in the vehicle. The center of gravity of a Tesla Model S is lower than that of most sports cars. Lower, in fact, than the Porsche 911, which famously places its engine behind the rear axle specifically to achieve good weight distribution. Tesla achieved something comparable without trying to. It was a consequence of the architecture, not a separate engineering goal. A low center of gravity changes how a car behaves in corners. It resists the tendency to lean outward as the vehicle turns, which is the physical sensation most drivers call body roll. Reviewers of the original Model S consistently noted that for a full-size luxury sedan, it handled with a precision that should not have been possible for a car of its dimensions and weight. The explanation was in the floor. The pack is also sealed, and the underside is a smooth, unbroken surface. No exposed components, no loose cables, no oil pan. This contributes to the aerodynamic performance covered later, but it also means the battery is protected from road debris in a way that a conventional engine compartment, full of exposed components, never could be. Inside each of those 7,104 cells, the same chemistry runs. It does not combust. It does not heat in any dangerous way under normal operation. It does something slower and far more controlled. It moves ions. The cells are connected by narrow ribbon-like cooling channels that carry liquid throughout the pack, maintaining every cell within a specific temperature range. Too cold, and the chemistry slows. Too hot, and it degrades. The thermal management system runs continuously, making small adjustments to keeping the pack alive and balanced. When the 85 kilowatt-hour pack was introduced in 2012 with the Model S launch, it represented the largest lithium-ion battery ever put into a production vehicle. At the time, analysts at Deutsche Bank estimated it would take the rest of the automotive industry at least a decade to match it. They were approximately right. Sitting above all of this, separated from it by a few centimeters of steel and sound-deadening material, is the driver. They feel none of it. The floor is silent. The floor is still. The floor is, in its way, the most important engineering decision in the car. What is inside each of those cells at the chemical level is where we go next. Lithium is the third element on the periodic table. After hydrogen and helium, it is the lightest solid material that exists. A block of lithium the size of your fist would weigh almost nothing. It is so light it floats on water. What makes lithium useful in a battery is a property it shares with most light metals. It wants to give away electrons. Hold a lithium atom next to an atom that wants to receive electrons, and the transfer happens readily. That transfer of electrons is, at the most fundamental level, what electricity is. The battery is simply a controlled environment for that exchange to happen in a repeatable way. In a lithium-ion cell, the chemistry works through a process called intercalation. The word comes from the Latin for to insert between. When the battery charges, lithium ions move through a liquid electrolyte from the positive electrode to the negative electrode, which is made of graphite. The graphite has a layered molecular structure so like a stack of pages in a book, and the lithium ions slip between those layers and sit there, held in place by weak chemical bonds. When the battery discharges, the ions flow back. As they move, they release electrons into an external circuit. Those electrons are the current that powers the motor. The lithium ions and the electrons are always moving together, just along different paths. The ions through the electrolyte, the electrons through the wire. Nothing burns. The electrolyte is not on fire. The graphite is not combusting. The reaction happens at temperatures close to the temperature of the room the car is parked in. It is chemistry happening slowly, reversibly, and in near total silence. A lithium-ion cell can complete this charge and discharge cycle roughly 1,000 times before the capacity begins to noticeably degrade. So Tesla's battery management software monitors each individual cell within the pack and adjusts charge rates and discharge limits to keep every cell within its optimal range, which extends the overall life of the pack significantly beyond what the raw chemistry alone would allow. Early concerns about lithium-ion batteries in cars focused on thermal runaway, a condition where one cell overheats and triggers neighboring cells to do the same, potentially causing a fire. Tesla addressed this through the physical separation of cells within modules, the liquid cooling system running through the pack, and software that shuts down cells showing abnormal behavior before they can affect others. No engineering system is infallible, but Tesla's thermal management architecture was, at the time of the Model S launch, more sophisticated than anything else in the automotive industry. The result of all this chemistry is a number, 85 kilowatt hours of stored energy in the original top-spec Model S pack. To put that in terms of familiar comparison, a typical residential household in the United States uses roughly 30 kilowatt hours of electricity per day. The floor of that car held nearly 3 days of home energy in a package the size of a large dining table. That energy sits there, stable, waiting. And how the car decides to use it, moment by moment, is not a question of chemistry. It is a question of software. The next part of this story is about the code that runs while you sleep. In May 2020, Consumer Reports published a test showing that the Tesla Model 3's emergency braking distance from 60 miles per hour was longer than expected. They flagged it publicly. Tesla's engineering team reviewed the data, and within 2 weeks, they pushed a software update over the air that reduced the Model 3's stopping distance by approximately 19 feet. No recall, no dealership visit, no new parts. The car got better while it was parked. Every car manufacturer in the world had, for most of automotive history, treated software as fixed. It was written, tested, and embedded at the factory. After that, it was permanent, unless a technician physically replaced a control module. Changing software after sale was logistically close to impossible, and financially close to unthinkable. Tesla treated software the way a phone company treats an operating system. The car is a computer that happens to have wheels. Like a computer, it can receive updates. Unlike a computer, so all those updates can change how fast it stops, how efficiently it uses energy, how well the suspension adjusts to road conditions, and how accurately the driver assistance system interprets camera data. Tesla delivered the first over-the-air software update to the Model S shortly after launch in 2012. In the years that followed, owners woke up to find their cars had quietly gained new features. A dog mode that maintains a safe cabin temperature for a pet while the driver shops. with a message on the screen telling passers-by that the animal is fine. A sentry mode that activates cameras when the car detects movement nearby and records potential threats. Suspension adjustments for known rough road sections based on GPS coordinates. A holiday light show. These were not features that existed at manufacture. They arrived later, silently, while the cars were parked. The implications for the automotive industry were disruptive in a specific way. A car's value in the traditional model depreciated from the moment of purchase. Every year, it was worth less than it was the year before, because a newer model existed, and the current one was falling further behind. A Tesla, in principle, could become more capable over time. The 2019 Model 3 that received the 2020 braking update stopped better after the update than it did when it rolled out of the factory. It improved. The over-the-air system also updates the neural network that runs autopilot. As Tesla's fleet accumulates more driving data, the pattern recognition models are retrained, and the updated models are distributed to every car simultaneously. A car manufactured 3 years ago and parked in a garage tonight may have substantially more capable perception software tomorrow than it has today. Tesla does not advertise this in the way you might expect. There is no press release for most updates. They arrive in the background, in the night, while the owners are doing something else entirely. The car tends to itself. It learns while you sleep. And in the morning, it is, in small ways that you may not immediately notice, slightly more than it was the night before. The question of how it sees the world it is navigating through is the next thing worth understanding. A Tesla does not see the road the way you do. You see continuous motion, context, and meaning. You know that a child running toward the curb is more dangerous than a plastic bag blowing across the lane. But you know this because you have a lifetime of experience telling you what children and plastic bags tend to do next. The Tesla has cameras. Current Tesla vehicles carry 8 cameras positioned around the vehicle, forward-facing at 3 ranges to cover near, mid, and far distance. Side-forward cameras mounted near the front doors, side-rear cameras, and a rear camera. Together, they give the car a 360-degree view of the environment. The images from all 8 cameras are processed simultaneously by Tesla's onboard neural network every fraction of a second. The neural network does not see objects the way a human would identify them. It processes the incoming image data as patterns and assigns probabilities. This cluster of pixels, moving in this direction at this speed, has a 94% likelihood of being a car. This shape at this distance has a 78% likelihood of being a pedestrian. Every frame, thousands of these probability assignments are made, updated, and acted upon. What the system is doing, continuously and invisibly, is making predictions. The car is not reacting to the world. It is anticipating it. By the time it decides to apply the brakes, the decision was already forming several frames ago, based on the trajectory the perceived object was following. Tesla calls this approach vision-based autonomy, and the choice was deliberate. Other self-driving development programs rely on LiDAR, which fires laser pulses at the environment and builds a precise 3-dimensional point cloud. Tesla's position, stated repeatedly by Elon Musk and by Tesla's AI leadership, is that the road was built for beings with eyes, not laser sensors, and that a sufficiently trained vision system should be able to navigate it, at least as well as a human can. Whether that argument is technically correct is a question the engineering community has debated at length. What is verifiable is that Tesla's camera-only approach has accumulated more real-world driving data than any other program of its kind. This brings us to shadow mode. Even when autopilot is not engaged and the driver is fully in control of the car, the system continues to run in the background. It processes the camera feed, makes its predictions, and determines what it would have done at every moment. Those decisions are compared against what the human driver actually did. Where they diverge, the data is flagged and eventually used to retrain the model. Every Tesla on every road, at every moment, is quietly running this parallel calculation. Millions of vehicles contributing to a single training dataset without the drivers knowing or needing to know. The cars are watching themselves learn. The volume of this data is the reason Tesla's system continues to improve at a pace that smaller fleets cannot match. A company testing 500 prototype vehicles on a closed track generates limited data. A company with millions of production vehicles on public roads generates data that is almost incomprehensible in scale. All of it flows somewhere, to a building in the Nevada desert that was designed from its foundations to be unlike any factory ever built. In 2014, the world produced roughly 30 gigawatt-hours of lithium-ion battery capacity per year. Tesla's plan, announced that same year, was to build a single factory that would eventually match that entire global output by itself. Tesla broke ground on Gigafactory 1 in Sparks, Nevada in February 2014. The site covers over 500 acres. The building, when complete according to Tesla's original design, would have a footprint of approximately 500,000 square meters, making it among the largest buildings by footprint ever constructed. Work on the factory began before the architecture was finalized. The first battery cells were produced there in January 2017. The factory was built in a specific way and for a specific reason. Lithium-ion cells are expensive, partly because manufacturing them is precision work. Tiny variations in cell construction affect performance, longevity, and safety. By designing the manufacturing process from scratch, inside a building designed around that process, Tesla and its battery partner Panasonic could control variables that were difficult to manage when sourcing cells from third-party suppliers. The design philosophy was vertical integration at a scale the automotive industry had not seen since the early days of Ford's River Rouge complex in the 1920s, where raw materials entered one end of the facility and finished cars left the other. The Gigafactory's version of this runs from raw cell chemistry through to finished battery packs, ready for installation in vehicles. The roof is covered in solar panels. The facility is designed to be powered entirely by renewable energy. The combination of solar generation, wind and geothermal sources available in Nevada was central to the site selection. Tesla's stated goal was a factory with zero net carbon emissions, making the battery that would reduce tailpipe emissions from transportation, using only clean energy to do so. At night, the building does not stop. Battery cell production runs continuously. The automation systems work in the same steady rhythm at 3 a.m. as they do at 3 p.m. There are sections of the factory floor where very few humans are present during a production run. Machines loading, monitoring, testing, and packing cells in a process that has been calibrated to reduce human variability. The scale of what happens inside is easier to hold if you think about it in terms of individual cells. A single 18650 cell is about the size of an AA battery. The Gigafactory was designed to produce tens of billions of these per year. Arranged end to end, the cells produced in a single day of full capacity operation would stretch for thousands of kilometers. Each of those cells will eventually sit in a battery pack in a car or an energy storage system, where it will be asked to charge and discharge in a stable and controlled way for years. The key word there is controlled, because the chemistry inside those cells is sensitive in ways that the factory's quality systems are designed to address before the pack ever reaches a vehicle. Temperature is the variable that matters most, and how Tesla manages temperature, both in manufacturing and in the car itself, is the next piece of this story. Lithium-ion chemistry has a preferred operating temperature, below around 10 degrees Celsius, and the ions move more slowly through the electrolyte, and the cell cannot deliver or receive energy at its rated capacity. Above around 45 degrees Celsius, the degradation of the electrodes accelerates, and the long-term capacity of the cell begins to shrink. The ideal window is roughly 20 to 40 degrees Celsius, which is close to comfortable room temperature for a human being. A car, however, does not live at room temperature. In northern Norway, where winter temperatures regularly drop to -20 Celsius, a Tesla sitting outside overnight will wake up with a battery that is too cold to perform well. In Phoenix, Arizona, where summer pavement temperatures can exceed 65 degrees Celsius, a battery sitting in a parked car is absorbing heat from every direction. Both conditions, if unmanaged, would shorten the pack's life significantly. Tesla addressed this with a liquid thermal management system, one of the first applied to an electric vehicle battery pack at production scale. A coolant fluid circulates through channels built into the battery module structure, absorbing or releasing heat as needed. The system can heat the pack when temperatures are too low and cool it when temperatures rise. It runs on electricity drawn from the pack itself, or from an external charger when the car is plugged in. The preconditioning feature works from this system. When a Tesla owner sets a departure time in the car's navigation or app, the vehicle begins warming or cooling the battery pack in advance, using power from the charger rather than the battery. The goal is to arrive at the departure time with the pack already within its optimal temperature range. A cold battery that has been preconditioned will deliver its full rated range. A cold battery that has not been preconditioned may show a range reduction of 20 to 40% on a very cold morning, not because capacity was lost permanently, but because the chemistry was temporarily sluggish. The same system manages the battery during fast charging at a supercharger. High charging rates generate heat within the cells. If the temperature rises too fast, the system automatically reduces the charging rate to protect the pack. Owners sometimes notice their charge rate slowing on a hot day, or after a period of spirited driving. And the reason is almost always thermal. The system is keeping the cells within the range where they can accept charge without damage. There is something calming about a machine that monitors its own condition this continuously. The human body does something analogous, sweating when too hot, shivering when too cold, sending blood to the core when the extremities need protecting. The battery management system is a slower simpler version of the same instinct. Protect the core, maintain the range, keep the chemistry stable. The thermal management system is always running. In a car that is parked and plugged in overnight, it is the only thing drawing power, running its quiet arithmetic in the background, keeping the pack at the temperature it needs to be at 7 a.m. when the driver opens the door and drives away. The battery is ready. And when that car eventually comes to a stop, something happens that most people never expect. It does not simply waste the energy of braking, it saves it. Every time a car brakes, it converts kinetic energy into heat. The brake pads press against the rotors, friction slows the wheel, and the energy that was moving the car vanishes into the air as warmth. In a conventional vehicle, this is simply how braking works. The energy is gone. It does not go anywhere useful. A Tesla does something different. When the driver lifts the accelerator pedal in a Tesla, the electric motor reverses its role. Instead of consuming electricity to spin the wheels, it becomes a generator. The wheels now spin the motor produces current, and that current flows back into the battery pack. The car slows down because converting motion into electricity requires force, and that force acts as resistance against the wheels. This is regenerative braking. The principle is not unique to Tesla. Hybrid vehicles use it too. But Tesla's implementation, particularly in its single-pedal driving mode, makes regeneration the default experience of the car rather than a supplementary system. Lift the foot and the car slows purposefully and smoothly, returning energy to the pack as it does. The efficiency gains are meaningful. In city driving, where a car accelerates and decelerates constantly, regeneration can recover enough energy to extend range by 10 to 20% compared to a car that discards all braking energy as heat. On a long descent from a mountain pass, a Tesla can arrive at the bottom of the hill with a battery that is slightly more charged than when it started the descent. Most Tesla drivers adapt to one-pedal driving within a few days, and many report that they miss it in conventional cars. So the sensation is of a car that feels continuous. There is no on and off, no moment where you move your foot from one pedal to another. You manage speed with one input, and the car takes care of everything else. The physical brakes, the calipers and rotors that exist in every Tesla for emergencies, and the small amount of stopping power that regeneration alone cannot provide, last significantly longer on Teslas than on conventional vehicles. Because the friction brakes are rarely called upon in normal driving, they see far less wear. Owners have reported brake pads still within service specification after well over 100,000 miles. There is a kind of arithmetic in regenerative braking that rewards thinking about it slowly. A car travels forward because energy was added to the system. That same energy, given a path back, can return to where it came from. The battery charges the motor moves the car's motion charges the battery back. It is not a perpetual motion machine. Energy is always lost to road friction and air resistance. But the loss is smaller, and the energy that would have become heat in a brake rotor instead becomes range. The result of all this, the motor, the battery, the software, the thermal management, the regeneration, is a car that consumes energy with an efficiency that combustion engines cannot approach. But that energy has to come from somewhere. It comes from a network of stations placed over more than a decade at intervals across the road systems of dozens of countries. That network is the next part of the story. In September 2012, then Tesla opened its first 6 Supercharger stations along a stretch of highway connecting Los Angeles to San Francisco. They were free to use, open to any Model S owner, and placed at intervals that made the drive between the two cities possible, without stopping for more than 30 minutes. There were 6 of them in the world. Within a decade, there would be tens of thousands. The Supercharger network is the infrastructure that made long-distance electric travel practical, and it was built almost entirely before there was enough demand to justify it. Tesla's position was that the network had to exist before drivers would trust the car enough to buy one. You do not build the roads after the cars arrive. You build the roads so the cars have somewhere to go. By the end of 2023, Tesla operated more than 50,000 Supercharger stalls across more than 5,000 stations worldwide. They appear at highway junctions, in shopping centers, at hotel car parks, and in the kinds of small towns that sit between larger cities and have historically been ignored by infrastructure investment. The placement is not random. Tesla uses anonymized driving data from its fleet to identify where cars actually travel and position stations accordingly. A third-generation supercharger, called V3, delivers power at up to 250 kilowatts per vehicle. At that rate, a compatible Tesla can add approximately 200 miles of range in around 15 minutes. The comparison to petrol refueling is not direct, because most Tesla charging happens overnight at home, and the driver never waits at a station at all. The Supercharger is for longer journeys, in the equivalent of a motorway service station, rather than the filling station around the corner. The station communicates with the car before the driver arrives. If the navigation system is set to route through a supercharger, the car begins preconditioning the battery as it approaches, warming or cooling the pack to the temperature that allows it to accept the fastest possible charge rate. By the time the driver plugs in, the battery is ready. The charging begins at full speed, rather than spending the first few minutes climbing to it. There is a gentleness to the way charge rate is managed. The supercharger delivers maximum power when the battery is below around 20% capacity. As the pack fills, the system automatically reduces the incoming power to protect the cells from the stress of high-rate charging at high states of charge. The graph of charging speed over time is not flat. It curves downward as the battery fills, the way a person might eat quickly at the beginning of a meal and slow down as they approach satisfaction. Tesla opened its supercharger network to other electric vehicle brands in several countries beginning in 2022, offering compatibility through an adapter. By 2023, Ford, General Motors, and several other manufacturers had announced they would adopt the Tesla charging standard for future vehicles, a development that positioned Tesla's connector design as the effective industry standard in North America. What began as infrastructure built to sell Tesla cars had become infrastructure the entire electric vehicle industry would rely on. The network exists now as a kind of nervous system laid across the roadmaps of dozens of countries, and the cars that travel along it were shaped at every surface by a discipline most drivers never think about. The shape of a car through air is not a cosmetic decision. It is an engineering one, and Tesla spent longer on it than most manufacturers thought was necessary. What they found in the wind tunnel changed the design of the car in ways that are invisible unless you know where to look. Air has weight. At highway speed, every surface of a car is pushing against it, and the air is pushing back. This resistance, called aerodynamic drag, increases with the square of the vehicle's speed. Drive twice as fast, and the drag force increases by 4 times. At 70 miles per hour, overcoming air resistance accounts for a significant portion of the total energy a car consumes. For a petrol car, this is a fuel economy concern. For an electric car, it is a range concern. Every unit of energy spent pushing through air is a unit that cannot move the car further down the road. This is why Tesla's engineering teams spent thousands of hours in wind tunnels, and why the shape of a Model S looks the way it does. The drag coefficient of a vehicle is expressed as a number, with lower being better. A brick has a drag coefficient of around 2.1. A typical family saloon sits somewhere between 0.27 and 0.35. The Tesla Model S, in its 2021 refresh, was measured at a drag coefficient of 0.208, which places it among the most aerodynamically efficient production cars ever built. This was not achieved by accident. It was the result of designing every external surface to manage airflow rather than simply enclose the car's contents. The roofline of the Model S descends in a smooth curve from the windscreen to the rear, guided by airflow data rather than stylistic preference alone. The underside of the car is completely sealed, a smooth, flat surface that allows air passing beneath the vehicle to flow cleanly rather than catching on exposed components. In a conventional car, the underside is a landscape of obstacles: the exhaust system, the differential housing, the fuel tank, subframe crossmembers. A Tesla has none of these, and the resulting smooth floor is worth a measurable reduction in drag. The door handles are retractable. When the car is in motion, they sit flush with the body, removing the small turbulent wake that a protruding handle would create at each door. They extend when the driver approaches. When closed, they disappear. It is a detail that saves an amount of energy that could be described as modest in isolation. But aerodynamic engineering is the accumulation of many modest savings. Every one of those decisions, taken together, adds up to a car that moves through air unusually well. Tesla's engineers also paid attention to the front of the car, which is the first surface air encounters. The lower front fascia channels air beneath the car and to the sides in specific paths. The wing mirrors, which are necessarily protruding, are shaped to minimize their wake. Even the tire sidewalls are considered. Tesla offers specific tire designs with aerodynamic wheel covers that reduce the turbulence created by spinning wheels, which is a larger source of drag than most people realize. The consequence of all this work is not just range. It is also the sound inside the cabin. Air moving cleanly over a smooth surface makes less noise than air catching on edges and gaps. The aerodynamic work and the acoustic work are the same work. A car shaped to waste less energy is also a car shaped to produce less wind noise. The 0.208 drag coefficient of the Model S means the car parts the air around it like something designed for it. Not disrupting, not fighting, just moving through. And inside, that smoothness translates into the particular quietness that people notice when they sit in a Tesla for the first time. That cabin quiet has its own engineering, layered on top of what aerodynamics alone provides. The walls, the glass, the floor beneath your feet. Each of them was treated to keep what little sound remains from reaching the person inside. When the engine disappears from a car, something unexpected happens. You start hearing things you never heard before. Not louder things, quieter ones. The faint sound of the tires on the road surface. The very soft movement of air past the mirrors. The occasional click of the car's thermal management system adjusting itself. These sounds were always there in a petrol car. The engine drowned them out entirely. In a Tesla, they are what remains. The acoustic engineers working on the Model S faced a problem that no car company had dealt with at this scale before. When the dominant noise source is removed, the remaining noises become prominent. Road noise and wind noise, which a conventional car masks with engine sound, suddenly needed to be addressed directly. The goal was not simply to be quieter than a petrol car. It was to be quieter in absolute terms. The windscreen and side windows on the Model S use laminated acoustic glass, the same type used in recording studios and high-end architectural projects. Standard automotive glass is a single pane or simple laminate. Acoustic glass adds a layer of polyvinyl butyryl film between two panes of glass, which absorbs sound vibration rather than transmitting it. Wind and road noise that would pass through conventional glass loses energy in the film and arrives at the driver's ear significantly reduced. The door panels are lined with sound-deadening material, and the floor beneath the carpet carries additional damping. Because there is no transmission tunnel running down the center of the car, the floor can be treated as a single continuous surface, which improves the effectiveness of the insulation, so there are no holes or gaps for noise to travel through that would otherwise exist to accommodate gearshift linkages or exhaust routing. The result, as independently measured by publications, including Car and Driver, places the Model S cabin at around 57 to 60 decibels at highway speed. The typical petrol-powered luxury saloon at the same speed measures between 68 and 72 decibels. Because the decibel scale is logarithmic, the difference between 60 and 70 decibels represents roughly a 10-fold difference in acoustic intensity. The Tesla cabin at 70 miles per hour is quieter than most offices during working hours. There is a physiological response to sustained low-level noise that most people experience without ever naming it. The body registers the vibration and the sound as background physical work, yet the kind of low-grade processing the nervous system performs constantly in noisy environments without the conscious mind being aware. Road trips in loud cars are tiring in a way that is partly explained by this. The body has spent hours managing stimulus that the mind was not tracking. In the quiet of a Tesla cabin, this load is reduced. Long-distance drivers in electric vehicles frequently report less fatigue at the end of a journey than they experienced in comparable petrol cars covering the same distance. The engineering explanation is acoustic. The human experience of it is simply feeling more rested upon arrival than you expected to be. The cabin quiet was designed. The laminated glass was specified. The sound deadening was measured and applied in targeted layers. The retractable door handles and the sealed underbody, which were aerodynamic decisions, also reduced the frequencies that passengers experience as wind noise. Each decision compounded the previous one. What had been engineered to help the car use energy more efficiently also, without being its primary purpose, made the interior feel like the quietest room most owners had ever sat in while moving. Below that quiet interior, the floor was about to be reimagined entirely. not just as a place to store cells, but as the structure of the car itself. On September 22nd, 2020, Tesla held what it called Battery Day at its factory in Fremont, California. The event was unusual for an automotive company. Rather than unveiling a new car, Tesla spent several hours explaining the chemistry and manufacturing science behind a new battery cell. The audience was investors and engineers, and the presentation lasted over an hour. At the center of it was a cell that most people in the room had never seen before. Tesla called it the 4680. The numbers refer to its dimensions: 46 millimeters wide and 80 millimeters tall. The older 18,650 cell that powered the original Model S was 18 millimeters wide and 65 millimeters tall. The 4680 is substantially larger, and the change in size is not cosmetic. Physics determines that a larger cell with the same chemistry can store more energy per unit of manufacturing complexity. More energy from fewer cells means fewer connections, less cooling infrastructure, and lower production cost per kilowatt hour. The 4680 cell also introduced a structural design change called the tabless electrode. In a conventional cylindrical cell, current flows in and out through small metal tabs welded to the electrode. In the tabless design, the electrode itself acts as the current path. This reduces internal resistance, which means less heat generated during charge and discharge, which means better efficiency and longer cell life. It also allows the cell to charge and discharge at higher rates without damage. But the deeper innovation announced at Battery Day was not the cell itself. It was what Tesla planned to do with it. In conventional vehicle construction, the battery pack is a module that sits within the car's structural frame. The frame carries the loads. The battery pack is a passenger inside it, protected but not contributing. Tesla's engineers looked at this arrangement and saw duplicated mass. The frame existed to carry loads the battery pack, if properly engineered, could carry itself. The structural battery pack eliminates the distinction between battery and floor. The cells are bonded together using a structural adhesive and integrated directly into the base of the car. The battery pack does not sit in the frame, it is the frame. In the Model Y, produced at Gigafactory Texas, this approach reduced the number of parts in the underbody by approximately 370 components compared to the previous design. The car became lighter, structurally stiffer, and cheaper to build simultaneously. Stiffer is a significant word in automotive engineering. A stiffer body structure improves handling precision, reduces the subtle flexing that creates noise and vibration over rough roads, and improves crash energy management. That the structural battery achieves these things not by adding material, but by making existing material do more than one job at once. There is an elegance in this that goes beyond the engineering. The energy source, the structure, and the floor of the vehicle are the same object. The car does not carry its battery. The car is partly made of its battery. The boundary between the thing that stores energy and the thing that protects the occupants has dissolved. Tesla began producing Model Y vehicles with the structural battery pack at Gigafactory Texas in 2022. The 4680 cells are manufactured at the same facility. From cell chemistry to finished vehicle, the process now happens in one location, using a manufacturing approach designed around the new cell from the ground up. At the car that first demonstrated it, was even possible for electric vehicles to be desirable was not the Model Y though. It was something older, smaller, and red. A car that launched in 2008 before most of the world believed any of this would work. The first Tesla Roadster was delivered to its first customer in February 2008. It was red. It was built on a modified Lotus Elise chassis, a lightweight sports car platform sourced from the British manufacturer Lotus. The body panels were made of carbon fibre. It seated 2 people and had almost no storage space. By every conventional automotive measure, it was a niche product for a niche buyer. What made it significant was not what it was. It was what it proved. The Roadster carried 6,831 lithium-ion 18650 cells arranged in 69 modules across the floor of the car. The total pack capacity was 53 kilowatt hours. The EPA-rated range was 244 miles on a single charge, which was more than twice the range of any other electric vehicle available at the time. The comparison point that most people used was the General Motors EV1, which had been crushed 6 years earlier with a range of around 100 miles. The Roadster covered more than double that distance and did it in a car that reached 60 miles per hour in 3.9 seconds. That 0 to 60 time mattered beyond the performance specification. The dominant narrative about electric cars in 2008 was that they were compromised vehicles, slow, limited, and practical only for short urban trips by environmentally motivated buyers who'd accepted reduced capability as the cost of their principles. The Roadster addressed this narrative directly, this not through argument, but through demonstration. Every automotive journalist who drove it wrote about the same moment. The moment they pressed the accelerator for the first time and felt the instant torque of the electric motor. The silence, the speed, the complete absence of what they had always understood as the feeling of a fast car, the rising engine note, the gear changes, the vibration. In its place was simply force, smooth and immediate, with nothing to listen to except the road and the wind. About 2,450 Roadsters were sold worldwide before production ended in 2012. The buyers included venture capitalists, technologists, and a number of celebrities. Several were bought as second or third cars by people who simply wanted to experience the technology. For many of them, the Roadster was the first electric car they had ever owned. For several, it was the beginning of a permanent shift away from petrol. The car had technical problems. The early transmission proved unreliable and required redesign. Customer service in those first years was inconsistent. The company was operating at the edge of its financial survival for much of the Roadster production period. Elon Musk later described Tesla in 2008 as being weeks away from bankruptcy on more than one occasion during the financial crisis of that year. The Roadster survived, the company survived, and what it left behind was a documented proof of concept. A lithium-ion battery assembled from cylindrical cells could power a sports car for over 200 miles. An electric drivetrain could deliver performance that equaled or exceeded what a petrol engine could produce. The engineering that Eberhard and Tarpenning had theorized in 2003 worked in the physical world. The next car Tesla would build would take everything the Roadster demonstrated and apply it to something the market could absorb at scale. Not a sports car for 2,000 buyers. A luxury saloon for everyone who had ever wanted a great car, regardless of what powered it. The Roadster also changed something harder to measure: the cultural perception of electric vehicles. Before it, an electric car was a statement of environmental principle. After it, an electric car could be a statement of performance preference. The two were not mutually exclusive, but the Roadster proved they were also not required to go together. You could want one purely because it was fast and beautiful, and unlike anything else on the road, that shift in perception is what made everything that followed possible. That car changed a question the entire automotive industry had been asking. And the answer arrived with a speed that no one in the industry had been prepared for. The Tesla Model S went on sale in June 2012. By the end of that year, it had won Motor Trend's Car of the Year award. In 2013, Consumer Reports tested it and gave it a score of 99 out of 100, the highest score the publication had ever awarded to any vehicle. When Consumer Reports tested a later version in 2015, the Model S scored 100 out of 100. A result the publication noted their scoring system had not been designed to accommodate. They adjusted the system. These were not scores given to the best electric car. They were scores given to the best car, in competition with every petrol and diesel vehicle on the market. The Model S was a full-size luxury saloon with seating for 5 adults and optional rear-facing seats for 2 children in the boot. It had a front trunk called a frunk because there was no engine occupying the space under the bonnet. The rear boot was full size. Total cargo capacity exceeded that of many estate cars. The range of the top specification model exceeded 300 miles. The performance of the base model surpassed that of most sports cars, costing twice the price. The automotive industry had spent most of the decade between the death of the EV1 in 2003 and the launch of the Model S in 2012, operating on a shared assumption that electric vehicles were a secondary market. They would serve buyers motivated by environmental concerns, who were willing to accept range limitations, reduced performance, and a smaller vehicle as the practical cost of their values. Nobody mainstream would choose an electric car over a good petrol car if the choice were genuinely free. The Model S made that assumption untenable. It was not a car that required a values-based trade-off. It was simply a very good car. Drivers who had no particular environmental motivation bought it because it handled better, accelerated faster, required less maintenance, and cost less to fuel than the petrol alternatives in its price bracket. The calculus of the purchase decision did not require ideology. It required arithmetic. The question the industry had been asking was whether people would buy electric cars. After the Model S, that question became irrelevant. The question became what the rest of the industry was going to do about it. The early answers were slow. Ford, Volkswagen, General Motors, BMW, Mercedes, and Toyota all had electric vehicle programs in 2012, but most were small, limited in range, and not positioned to compete with the Model S directly. The internal reasoning at most manufacturers was that the premium electric market was Tesla's for now, that mainstream buyers would not follow, and that a measured response over the following decade would be sufficient. That reasoning held until roughly 2017, when Tesla's production of the more affordable Model 3 began, and the waiting list reached 400,000 reservations. At that point, the measured responses accelerated rapidly, and the full-size luxury saloon that started all of this had done something unusual in the history of industrial competition. It had not captured market share from existing competitors. It had demonstrated a technology so effectively that the competitors were forced to abandon their existing products and rebuild their entire manufacturing capabilities from the ground up. What followed was not a ripple. It was a restructuring of one of the largest industries in the world, and it happened with a speed that the people inside that industry had not predicted and could not fully control. The Model S did not just sell well. It altered the competitive logic of an entire industry in the space of a few years. And the manufacturers who had held back their responses found themselves arriving late to a transformation that had already moved past. The point where catching up was straightforward. In 2015, there were no serious long-range electric vehicles in production from any of the major automotive manufacturers. Volkswagen, the largest car maker in the world by volume, had no battery electric vehicle in its lineup, with a range above 100 miles. Ford's electric vehicle was a converted version of its Focus compact car. General Motors had the Spark EV. None of them were built from the ground up as electric vehicles. All of them were petrol platforms, adapted to carry a battery. By 2023, the same companies had committed hundreds of billions of dollars to electric vehicle development and had fundamentally reorganized their manufacturing operations around the transition. Volkswagen Group announced it would stop selling combustion engine cars in Europe by 2035 and committed to building 6 battery cell factories in Europe alone by that date. Ford announced a $50 billion investment in electric vehicle and battery manufacturing through 2026, the largest single commitment in the company's history. General Motors announced plans to eliminate petrol and diesel vehicle production by 2035 and committed to launching 30 new electric models globally by the end of 2025. Stellantis, the group that owns Jeep, Fiat, Peugeot and Chrysler, who announced that all its brands would offer electric versions of every model in their European lineup by 2025. These were not incremental adjustments. They were structural transformations of companies whose entire manufacturing base, supplier networks, workforce skills, and business models had been built around the internal combustion engine over the course of a century. None of it happened because of regulation alone, though regulation was part of it. It happened because Tesla had demonstrated, with a decade of production data, that drivers would choose electric vehicles when the vehicles were good enough. The Model S, the Model 3, the Model Y, which became the best-selling car globally in the first quarter of 2023, had each answered a version of the same question. Yes, people will buy this. Yes, at scale. Yes, in preference to petrol. The manufacturing challenge the rest of the industry now faced was daunting. Building a battery electric vehicle requires a fundamentally different factory than building a combustion engine vehicle. The engine, transmission, and exhaust system, which represent the majority of the complexity in a petrol car, are replaced by a battery pack, an electric motor, and a power electronics unit. The tooling, the supply chain, the workforce training, the quality control systems, all of it different from what the existing factories had been designed to do. Some manufacturers managed this transition more effectively than others. Some built genuine competitors. Others produced electric vehicles that fell short of the range and performance benchmarks Tesla had established, and found that buyers, once they understood the specification gap, were unwilling to accept it. The competitive dynamic created by Tesla's entry into the market was not traditional. Tesla did not take customers from Volkswagen by offering a better Volkswagen. Tesla redefined what the product category could be, forcing every other participant to respond to a standard they had not set and had not seen coming. The roadmap of the industry now runs toward electric, not as a side road for the environmentally committed, but as the main road for everyone. The transition is uneven. It is proceeding at different speeds in different countries, and the full consequences of it are still unfolding. But in the places where electric vehicles have been adopted at scale, something measurable has already begun to change. Not just in what the cars are, in what the cities around them feel like. The transformation is audible, if you know where to listen. It is breathable, if you know where to look. And it began with the same question that two engineers asked in California in 2003, before a single Tesla had ever turned a wheel. Norway made a decision in the early 2010s that most countries were unwilling to make. It exempted electric vehicles from the taxes and fees that made car ownership expensive there, offered free parking in many city centres, and allowed electric cars to use bus lanes. The incentives were significant enough to change behaviour at a national scale. By 2023, more than 80% of new car sales in Norway were fully electric, the highest proportion of any country in the world. Oslo, the capital, had effectively become the first major city where the electric car was not an exception, but the norm. The change was not only statistical, it was physical. Internal combustion engines produce emissions that include nitrogen oxides and fine particulate matter alongside carbon dioxide. These compounds are responsible for a measurable portion of urban air quality problems. Fine particulates, those smaller than 2.5 micrometers in diameter, penetrate deeply into lung tissue and have been linked by the World Health Organization to respiratory and cardiovascular disease. Cities built around heavy car traffic have historically carried elevated concentrations of these particles. As electric vehicle adoption in Oslo accelerated through the 2000s, researchers at the Norwegian Institute of Public Health and the Institute of Transport Economics began tracking air quality data. Studies published through this period documented reductions in nitrogen dioxide concentrations in central Oslo as EV adoption increased. The relationship was not perfectly clean. Other factors, including changes in heating systems and public transport, contributed. But the directional signal in the data was consistent. Fewer combustion engines in the city correlated with better air. The sound changed too. This is harder to measure than air quality, but easier to experience. A street where most of the traffic is electric has a different acoustic texture than one dominated by combustion engines. The tire noise remains because physics does not allow rubber on asphalt to be silent. But the engine note, the idle rumble at traffic lights, the burst of acceleration that accompanies a gear change, all of that is absent or greatly reduced. What remains is a quieter, lower, softer version of the city. Residents of neighbourhoods with high EV density in Oslo described the change in interviews and surveys not always in technical terms, but in felt ones. Less aggressive, calmer, easier to have a conversation outside. Children playing near streets, a thing that urban planners had begun to design away from in recognition of noise and emissions becoming more possible again. The physics of what produced this change is exactly what has been described throughout this story. The AC induction motor that Nikola Tesla patented in 1888. The lithium-ion chemistry that stores energy without combustion. The software that manages both with a precision that no mechanical system can match. Each of these things, working together in millions of vehicles, is producing an aggregate effect that one vehicle could not. The transition is not complete. It is not even close to complete on a global scale. Combustion engines will continue to operate on the world's roads in large numbers for decades. The change happening now is the beginning of a direction, not the end of a journey. But the direction is set. The question that the automotive industry spent most of the 2000s arguing was unanswerable has been answered. And in the cities where the answer has already arrived in sufficient numbers, the people who live there are breathing something slightly cleaner, hearing something slightly quieter, and sleeping in something that was, not very long ago, only a theory. That theory started with two engineers in California, a name borrowed from a dead inventor, and a question about what might happen if you put laptop batteries in a car. We started this story in a car at rest. No idle, no vibration, no mechanical pulse moving through the seat. A machine that was on and alive and doing its quiet work without announcing itself to anyone nearby. That silence, the particular absence of sound that people describe the first time they sit in a Tesla, was the beginning of a thread that turned out to run through more than a century of human invention. It runs back through the gigafactory in the Nevada desert, where cells are born in their millions and distributed to vehicles across 6 continents. Back through the software update that arrived in the night and made a car stop better than it did when it left the factory. Back through the 8 cameras reading the world as probability, as building a picture of the road from light and mathematics. It runs back further to a factory in Fremont, California, where the Model S was assembled and tested and driven out onto a road for the first time, into a market that had been told for a decade that nobody would buy one. Back to the Roadster and its 6,831 cells, and its first delivery in February 2008 to a driver who pressed the accelerator and felt something unprecedented. Back further still to 2 engineers in San Carlos in 2003, choosing a name from a history most people had forgotten. And back to the man behind that name, a Serbian immigrant standing in a laboratory in Manhattan in 1887, watching a rotor turn inside a magnetic field, understanding that he had found a way to make motion out of nothing that could be seen or touched. Nikola Tesla died in 1943 without knowing that the principle he had discovered would eventually power millions of vehicles on roads that did not exist in his lifetime. He could not have imagined the battery pack lying flat in the floor of a car, or the software that updates it in the night, or the supercharger stations placed at intervals across deserts and mountain passes and motorway junctions in countries he never visited. He understood the motor. He understood the field. He understood that magnetism and rotation were the same thing expressed differently. That was enough. The rest followed, slowly, over the following century, one engineer's contribution at a time. The silence inside a Tesla is the accumulation of all of that. Every decision to remove a source of noise, every choice to replace combustion with chemistry, every line of code written to manage a system that a mechanical engineer of the 1950s could not have conceived. Taken together, they produced a room that moves, a quiet space that happens to be doing 70 miles per hour. If you are still awake, that is where you are going, toward quiet, toward rest. The kind that comes when the systems around you are doing their work so well that there is nothing left for you to manage or respond to. The cars are charging in the dark outside cities on every continent. The software is updating. The batteries are being kept at the temperature they need to be at. The thermal management systems are making their small adjustments. The gigafactory is running. The cells are being born. And somewhere, in a street that is slightly quieter than it was 10 years ago, in a city that is breathing something slightly cleaner than it used to, a person is asleep. If tonight's story left you with something worth carrying into sleep, Simple Science has more waiting for you. Subscribe so the next one finds you. If this helped you rest, a like is the quietest and kindest way to say goodnight. We will be here tomorrow with something just as worth knowing. Sleep well, wherever in the world you are.